before I start with science, I think it is a good opportunity and a good, say, social surroundings to say a few personal remarks, because our meeting here is in honor of you, dear Karl-Heinz. And when I think back to the times when our personal relationship was, at the beginning was a scientific one, but I think very quickly changed into something else, started, then I still not without wonder about the fact that you back then really took the risk and accepted me as a PhD student, although I was not a physicist at all. So then accept my deep gratitude for the chances you opened for me. And when I started my studies then as a student, step by step I learned, of course, your way of teaching, your way of arguing, your way of doing research. So that is, in one word, your way of thinking. And then it was not only once that I got remembered of what I had read about. I had read about Jon von Neumann, this famous mathematician. It is told that his co-workers and students often said after discussion with him or after a lecture, "Oh man, this is just the way, if it comes to thinking, this is just the way one should think." And I think it is in a high degree, it is true for you. It's your thinking demonstrates the way one should think. And this is not only science, I think. I personally hold it for something for true, which is sometimes is point to be the totality of the personality. Maybe it's a heavy word, which means that if somebody shows particular clarity and a clear sense of what is right and wrong in his professional field, then it is very likely that this does not stop at the margins of his field, but extends to other areas of human affairs. So let me tell a short story. It once happened that your youngest son, Hans, during a political demonstration, experienced a very rude and, in fact, illegal behavior of the police forces. But he could not complain about that. He could not accuse somebody because the policemen failed to wear their numbers on their uniforms, which was declared mandatory by law at this time in the state of Brandenburg. And then you felt it not to be a waste of time to sit down and write a letter to the authorities with an appeal or a request for a justification of the circumstance. And I remember well how deeply upset you were when the response came, and the response said, "Oh, this law, yeah, it does exist, but it is anyway planned to abolish this law next year, so our policemen stopped to wear this number." So you were so upset because I think you have a strong aversion against any sort of intellectual, of any missing of intellectual righteousness, of any intellectual dishonest. So that's why I think both in science and in human affairs, there's still a lot of things we have to learn from you. And I wish you lust for life, health, and a lot of strength for many coming years.
And it was always a pleasure for me to have contact with you in scientific and in not scientific things.
Thank you. Yeah, now I come to test methods, and as many ideas in the field, we owe it to some extent to Karl-Heinz again, because I remember well that very often in lectures and discussions he said it should be possible to measure these coefficients by applying different sorts of mean fields to the turbulence or the velocity field it is. And in fact, it's almost now 40 years ago that to some extent this idea was really realized in the famous Alpha Yashik in Riga, I think, yeah, where people constructed a box, that's the meaning of Yashik, where an intricate flow was designed in it, and then they applied the mean field and really could measure then a mean electromotive force and derive from that the alpha effect. And then much later, as many of you know, Dieter Schmidt and Göttingen came up with the idea to charge a PhD student with that task. This was Martin Schöner, who is here today. And then work started and went on very quickly, thanks to Martin. And we now have something, I think, which is really good established, well-established method, the so-called, we call it sometimes, so quasi-kinematic test field method, where it is assumed that the velocity field is essentially given, that is existing already without the presence of a mean field, and that under these circumstances we can very reliably determine the mean field coefficients, even in the case that this velocity is already somehow influenced by the mean field. So that we, by this method, are really able to derive already quenched mean field coefficients. So there was a debate about that, but I think it's step by step now becoming more or less established that this theory is reliable, and we have already heard some examples for that during this meeting. But what about other cases, which should find our interest too? What about background turbulences, not on background in the sense existing already without the mean field? Background turbulence which contain not only a hydro but also a magnetic part. Or what about the purely hydrodynamic setup, where we want to ask for mean field coefficients for the velocity, that is turbulence, viscosities, and so on. And these two topics are what I want to speak about today. So a short outline, very briefly give a motivation, then come to the first case where the background consists of a real NHD turbulence. Don't take the word turbulence too serious. No, I use it simply as a synonym for fluctuations, for anything what is not an average. It's not. So, Igor, don't look too critical. It's only a word. It's only a word. Then in the last part, then I will speak about preliminary results about a test fields method for hydrodynamics. Yeah, where does the motivation comes from? I think we should cope with this problem. Mean field NHD models with a predictive potential. Somebody might say, I heard this opinion, that this is overambitious, but I could respond if somebody is really bold enough to take a big heap of money from the European Union. One should be brave enough to face this task. Because at the end, I think if solved, if answered, then it would give a chance to have a predictive model of the solar dynamic. I agree it is very ambitious. So what do we need for that? What we want to know on this behalf is an expression for the mean electromotive force and mean ponderomotive force. Don't worry about units here. I've made my life simple. V has a unit of velocity and J has a unit of field divided by length. And of course, these are only identities, and they are only of benefit if we are able to relate them to the mean quantities. That is, if we were able to write something like that in an explicit form, both EMF and force as functionals of the mean quantities. And what are the requirements for that which we can formulate today? This is clearly, they have to be nonlinear. They have to be non-local, that is, the coefficients which are in them need to be somehow scale dependent, and likewise not instantaneous, that is, they have to include some sort of memory effects, which are already, at least the later two, well studied in the kinematic setup. So only for repetition, I recall the quasi-kinematic test field method now. We start with these so-called test problems, which are in fact nothing else than the equations for the fluctuating magnetic field. They have the same mathematical structure, except that there's on the right-hand side, in place of the mean field, now a test field. It is a mean field again, of course, too. But we have that index, so it's not only one, it's a whole series of test fields. And we solve these test problems for test solutions pk for a whole series. And then we calculate the mean EMF for each of these solutions, and finally obtain by inverting this ansatz or equation system, if you want, for these desired quantities alpha and beta. And we know that the solution is unique if we have enough test fields, n is big enough, and the test fields are sufficiently independent in order to avoid a singularity in this equation system. What now if we admit an MHD background turbulence? That is a turbulence where, if we decompose the fluctuating fields in a part each, which does not depend on the mean field, and it does depend on it, and here again for B, in which U0 and B0 are at the same time non-vanishing. This, of course, then the next idea which comes to our mind is that this is due to a small-scale dynamo. But it's, for experimental purposes, of course, we could think about an electromotive force which drives the B0 part. So here I demonstrate why the usual, the quasi-kinematic test field method must fail in this respect, because if you write down an equation for this part of BB, which is the interesting one, then we see that, except from terms we already had and which are not a danger really, these, and this one, we have another one where this quantity UB occurs. And it's impossible to solve this equation without having it in the hand, except we make the so-called second-order correlation approximation. In this case, the whole bracketed expression here with the dash would disappear, and the solution would still be solvable. But if it comes now to calculating the mean EMF, which is of this form, then we desperately need this UB, and we cannot recover the full EMF without having it. So there is no chance in this setup, even in SOCA, to calculate the coefficients by the usual test tube method. And if we go beyond that, we are of course faced by the basic challenge that we need to have a method in which the part of electromotive force, which depends on the mean field, turns out to be linear and homogeneous in the mean field. Because this is just a prerequisite of any test field method. So, want to demonstrate how to overcome this difficulty for a model problem with a simplified MHD. So you see here that the momentum equation has been cut. There is no advective term and no pressure term for simplicity. This is the induction equation formulated in the usual way, but for the vector potential. And that indicated the units. And this has gives the opportunity to study it without having several nonlinear effects here. The only nonlinear effects coming from these two bilinear terms. And it's still something like dynamo action possible in this problem, so we don't lose really a lot of facets of the physics. And what we want to find, or what we want to represent at the end by mean field coefficients, are these two quantities now: the mean electromotive force caused by the mean field, and the mean ponderomotoric force caused by the mean field again. And here are the expressions for it. And analogous to what we already do all the day for the mean electromotive force, the ansatz which we usually employ for it, analogous ansatz has of course to be made for the mean ponderomotoric force, excuse me, which is, you may wonder a bit why it is linear and be mean here, but I will come to that point. It's not a contradiction. I think I'll skip this transparency and now show you how the idea goes on. So we first decompose the problem for the fluctuations into different sets of equations. First, one set for the zero quantities, which means for those quantities which exist already in the absence of the mean field. And you see here are forcing terms, so they can well be caused by something, and this force might be absent, so then it could be a small-scale dynamo. And this system is clearly closed and may live on its own and can be quite independently solved. And then we have another set of equations for the quantities UB and AB, which depend just on the mean field. And up to now, these two groups of equations are just equivalent to the original systems. No approximation or not any weird manipulation has been done. It's simply equivalently reformulated. If we now rearrange in the equations for UB and AB, the nonlinear terms in the following way. So first I have introduced these symbols here for the nonlinear terms. All the other terms are linear, as you see, because here we have the B fields. But these are the nonlinear terms, which usually are neglected in second order correlation approximation. And now we see that we can rewrite them in this way. Here, usually there were 3 terms. Now there are only 2, because I have at this place, for instance, I have put together again J0 and JB, and analogous in all the other places. And analogously, of course, for the mean electromotive forces. Again, the same story, regrouping some of the terms. And if you know, this is really the decisive and questionable, I did not admit that, questionable step. If you are bold enough to say, we identify now the quantities U and B with the fluctuating fields, with the turbulences in the so-called main run, so in the original magnetohydrodynamic simulation of a certain system, and forget the relationship between B0, say, BB and B, then we arrive at the system, and you have it now before you, which all of a sudden turns out to be linear in the unknown quantities, UB and AB. And these solutions are in turn linear and homogeneous in the mean fields. And for that reason, the mean electromotive force or the ponderomotoric force are then linear and homogeneous in the mean field. And this is just the condition for the applicability of any test field method. Yeah, this is simply rewriting this in terms of test equations, the same system as you have already seen. Now you have here, instead of the mean fields, these indexed mean fields, which means these are test fields. The mean flow is here considered as a parameter of the problem, or as exactly that mean flow which comes from the main run. It is not a test field method here for where the mean flow is considered as the interesting quantity from which the mean forces should depend. The mean forces here depend completely only on the mean field, and this U mean is a parameter. And here I have repeated these reformulations of the nonlinear terms, and you see that we, by these different combinations, now have in total 4 different flavors of a test field method, because we can combine any of these 2 with any of these 2. And that's why we get 4, and they can be labeled in a way which is indicated here, but I skip this, it's not very important. Anyway, this defines a system of test problems or test equations which need to be solved in addition simultaneously with the main run. Of course, it will extend the numerical work considerably. Some remarks. The coefficients, these 2 for the EMF, these 2 for the ponderomotoric force, they will not depend on the test fields. They will reflect properties of the fluctuating fields from the main run and of the mean flow there. And if they are affected somehow by the mean field, and this is true in fact for the mean velocity too, then the tensors will reflect this dependency in the sense that these tensors will become dependent on the mean field of the main run, not dependent of the test fields. And I'll skip this. And then consider SOCA, second order correlation approximation, if one neglects those nonlinear terms in the test programs, or if one assumes kinematic, that is, the mean field goes to 0 and the fluctuating fields goes to their undisturbed original fields, then all the 4 versions melt down to 1. And one further remark, if we set now deliberately the B0, that is the magnetic fluctuation in the absence of the mean field, to 0, then one of the 4 flavors falls back to the already known quasi-kinematic method, which are all good arguments for validity, but we have no rigorous argument for the equivalence of the 4 flavors of the test field method, and we have no rigorous argument for the same reason, in fact, why this method should at all deliver correct results. So, we have had to check it simply. because we are not mathematicians enough to figure this out theoretically, whether there is any value in this method. Yeah. Now we turn to planar averages, that is here x and y average. So all mean quantities are defined by averages over all values of x and y, or in other terms of all x and y in the periodic box where the simulations are usually done. And then we can simplify it somehow, because here now the current density occurs instead of the derivative tensor of B, and here again. And we have to deal with these tensors phi, c, alpha, and eta, which now each of those now have only 4 interesting components. The remaining ones are either 0 or not interesting. And in total, that's why we have 16 components to determine, and we need 4 test fields for that. As an example, I will consider something which is not even nearly a turbulence, but instead it is in some sense, of course, a laminar flow, namely the famous Roberts one, which is connected to the Blind Roberts, not the Paul Roberts, and was one of the first laminar flows who showed dynamo action, but not the very first, in fact. It has a very simple geometry with a z component and 2 circle components, and the important thing is it has helicity, and if we set this parameter sigma to 1, then it has even maximal helicity. It has the Beltrami property, and as a consequence, if one would force both hydro and a magnetic fluctuating field with this geometry, then they would not interfere. So U naught cross B naught would not give anything, and J naught cross B naught would not give anything which would disturb the system. Here, once again, the geometry of it in over one period, which is in fact just the box we have used for the simulations. So color means here the z component perpendicular to the screen plane, and you see the arrows for the remaining 2 components. This is one of the Roberts flows. Roberts in fact has considered several patterns. That's only one of them. And now results. First, we return in some sense to, not in some sense, indeed, we return to the case where already the quasi-kinematic method that does the job, that is purely hydrodynamic forcing, and we consider the kinematic case where the mean field is in fact 0 or goes to 0. And we have here in red the results of the new method, that indeed of all 4 flavors of this method. And they all indeed agree, and they agree further with this blue line, which represents the analytic Sokar result for that flow. And they further agree, but is not depicted here, with the results of the so-called imposed field method, which works with imposing a mean field into the main run instead of having separate test problems to solve. So everything is fine here. And the next case, of course, is the complementary one, where the turbulence is not purely hydrodynamic, but purely magnetic. And this we have really performed by introducing forcing an electromotive force in the system, which just creates a magnetic field E0 of the shown geometry. And you see again here the numeric result of the method, the Sokar result, and they agree as far as they should, and they start to disagree where one would expect that they start to disagree. Somewhere between 0.1 and 1 here, and here it's similar, where the relevant parameters here, of course not the magnetic Reynolds number, but the Lundquist number, which is defined in a very analogous way. Now coming to the combination of both. So we have both forcings, both fluctuating fields, U naught and B naught in the system. And first consider the alpha tensor. As I said, for the Roberts geometry, these 2 fields are mutually uninfluenced, even if they both exist at the same time, forced at the same time. They would not interfere. So a naive idea, and what is really true in Sokar, means that then alpha should be simply a superposition of the two contributions, one coming from the case where the magnetic background is 0 and the other from the case where the hydro background is 0. But if one goes beyond the second order correlation approximation, say to fourth order, one sees immediately that there is an additional contribution. Oh, sorry. Yeah. An additional additional contribution. So we coined it magnetokinetic in that case, which is quadratic in both amplitudes. So it disappears if only one is already 0. But this cannot be detected in soccer. And the numeric results is shown here. Here we see the total alpha which is measured. It changes sign at this place. And it was assumed that the forcings are equal. That's why we have magnetic Reynolds number and Lundquist numbers equal. And we see that the two parts are behaving. This is magnetic and this is kinetic. And the sum of them, that would be the naive or soccer guess for the result, is really behaving differently. It's simply growing at this curve, where the actual result is growing a bit, then falling and changing sign. And we have checked this against the fourth order calculation, especially this part alpha mk, which is shown here. And it's shown here once again in comparison to the analytic calculation, which is the blue line. And we see that it coincides where it should, but it starts to branch off around 1, which again confirms that higher order calculations, which can be done analytically to some extent, are not really yielding a big gain because the convergence is obviously slow. We have not extended the validity range very much, only to something around 1. But numerically, we can get these values, of course, for higher values. And as a consequence or conclusion from that, I wanted to stress that we have seen here, because we have seen here a part, this alpha mk, this part, which makes the behavior of alpha quite different from what is expected. That is dangerous to apply closure approaches where not the correlations up to the fourth order are included, because we see here the fourth order correlations are really important. As one, at least as somebody believed that the sign of alpha is important. But I think it is. So this gives, in some sense, the hint that we should think about closure approaches which go beyond that and maybe make an ansatz for the fifth order correlations only for simplification, but not for third or fourth order correlations, at least in a setup like this. And now to the other two tensors which are interested in this case, again for hydromagnetic forcing, so both background turbulences should exist. But now we are interested in the two tensors which describe the mean ponderomotive force. And here we have to notice first that because this force is the divergence of the magnetic stress tensor, which is I showed here, it needs to be 0 if the mean field is 0. So we have to conclude that the tensor phi is 0 if B is constant. And in other terms, that if we make it k-dependent, scale-dependent as in the test field methods the case, then it should go to 0 if the wave number goes to 0. Now, of course, it's interesting to have an analytic result, and this is easy to get. So these are the soccer results for this case for phi, and psi turns out to be 0 if the flow, the Roberts flow, has maximum helicity in that case. So we have this result, we see this bilinear, this both amplitudes fit in, and the behavior we expect is really found. Because if k goes to 0, these components go to 0, as they should. And in physical space, we could approximate them the following way. If k goes to 0, we could model them as a second derivative of the mean field. And if k goes to infinity, we could model this part of the force simply by the mean field itself. So this, which modeling is the right one depends on the scales. And now again, comparison between the SOCA and the numerical results. When we have all four tensors, which are still isotropic. That's why I've shown only one value here in each case. And the blue lines are the SOCA results, and the red dots or red symbols are the numerics results. And we see, yeah, as I should say, the labels on the curves are the magnetic Reynolds numbers or Lundquist numbers, which are for these three panels the same. And we see that there's good agreement, except for the last curve in each panel, which just belongs to the highest magnetic Reynolds number, which is around 5. And so it's not a surprise that we leave the validity range of SOCA. And the last panel is shown the quantity psi, which should be 0, but it's no longer 0 if the helicity of the Roberts flow is not maximum. And this is, again, there is a SOCA solution for that, and I show again here for two cases of two different magnetic Reynolds numbers, agreement for low values and disagreement for higher ones. But it's still not that bad for high K. Now, of course, more interesting, because as long as we are in the kinematic case where the mean field does not considerably act on the flow at all, much more interesting is what the method still can yield if we leave that more or less safe ground into the nonlinear world, where we have not really a good mathematical justification of the method. And we have here considered again the same robust geometry in the fluctuating fields. This is not changed, but we have allowed for a mean field here in x direction in the main run. And of course, this causes some anisotropy. For instance, for the alpha tensor, if it was isotropic in the plane, I must say isotropic before, it had only this part. Now it will attain this part because the mean field adds some additional direction. Here, these are the unit vectors of the mean field. And at the end, we get again a scalar relationship between the mean ENF and the mean field. This is because this anisotropic part of the tensor degenerates if dotted with the field itself. So we get here the sum of both coefficients in this scalar relationship. Yeah, we have done again we've studied again these three cases. Purely magnetic forcing first. Here we see that the RMS value of the magnetic turbulence is constant for a while, and then with increasing mean field is decreasing, whereas the URMS, which is not, U is not existing at the beginning. So it's, for external field equals 0, it would be 0, but in the course of the growth of the imposed field or the mean field, URMS is growing, reaching a maximum and then falling again. And here we have the alpha, which is really the sum. One of these curves is really the sum of these two. So focus on the red curve here. And this has this behavior, which is, firstly, it's important to say, completely confirmed by the imposed field method. As long as the imposed field is weak enough, we can do that. And secondly, we see here that the best fit would be that the coefficient falls with the fourth power of the mean field, which is in fact a bit surprising. And here the other two cases, this is purely hydrodynamic forces, and in some sense confirms already known results, because this case can be done with the already existing method. And we see the same behavior. And finally, also in the case of combined forcing, we see the same behavior again for the efficient alpha, just the alpha which acts at the end between mean field and mean ENF. But we see a somewhat different behavior for that part of alpha, which is shown here. Yeah, I said it's somewhat surprising because theory up to now has delivered us two results, namely b to the second and b to the minus second, b to the minus third. But it's quite clearly that this cannot be the case, and it was even seen for another flow, namely for the ABC flow, that this power law should be b to the minus 4. So any proposals welcome at this place? Yeah, let me at this point summing up what we can say about this branch of the method. We have an agreement with the opposed field method as far as this can be checked. We have agreement of all 4 versions, all 4 flavors of the test field method. We do see sometimes various instabilities if the mean field is too strong, but there's some idea that this could be a numerical effect. We have agreement with soccer calculations as far as available. We detect a new part in the alpha effect, which cannot be detected in soccer or any closure which is not considering fourth order correlations. And we see this strong quenching. Now we'll come to the second field, namely isothermal compressible hydrodynamics. Now the equations are more honest than before. It's no longer a simplified model problem. You really see that everything is fine as long as we can assume that we have isothermal conditions, so the sound speed is constant. And the hydrodynamics is here formulated with the enthalpy, which is essentially the logarithm of the density. So the ideas or the way of derivation goes the same path. So we decompose again the fields in a part, not depending now, of course, on the mean flow, and one part depending on the mean flow, and another, and here the same. And we have again, of course, for the background turbulence, U0 or U0, H0, again a closed system, namely this one, where forcing is set in. So this system can be solved completely, isolatedly. I should mention that the dash here means stripping out the fluctuating part. It's an operation to be really performed on these expressions everywhere. And maybe I should mention further that you might be a bit wondering what this means. This comes from the fact this part in the dissipative part of the equation comes in fact from our assumption that the kinematic viscosity is constant but not the dynamic one. That's why here there's an additional gradient of the density effect occurring. Yeah, these are the equations for those parts of the fluctuating fields which depend on the mean flow, UU and HU. And I've marked here with this darker color the terms which we would like to neglect in something which is, that again, a second order correlation approximation, so that only these parts would remain. And reduce the abbreviation. And we cannot perform, well no, first we have to write down the mean force, which you're really interested in. Again, it has 2 parts, one part not depending on the mean flow, but for the moment being, I will assume that this part is simply vanishing. And then the other one is consisting of all contribution from all the nonlinear terms which occur in the equation. And the same is true for the mean source of enthalpy in this case. We have a second quantity. This is enthalpy, and this second quantity again experiences or sees the occurrence of an additional term in the equation for its mean, and this is the source term which would occur in the equation for the mean enthalpy. And again, of course, defined by the nonlinear terms which occur in the enthalpy equation. Correct. Yeah. Oh, I should skip this. And it's coming now to the same trick, or as you want, boldness to regroup the terms to produce something which is apparently, or seemingly, if you want, linear in the fluctuating field. So we have this nonlinear term, for instance, and we regroup it in, for instance, the way that we add up U0 and U here to get this form, or to add up UU and U0 here and get this form. And the same can be done for all the nonlinear terms which occur. This was the second one coming from the dissipative term, and this is coming from the enthalpy equation. And in each of these cases, we have two different choices. So in total, we have 8 combinations. And now, again, we do this a bit questionable step to say that we identify U and H everywhere with those quantities which are found in the direct, in the main run, in the direct numerical simulation, and forget about the relationship between this quantity U, say, and U naught and UU. And again, the result is just the same as before. The differential equations for UU and HU now become linear, and the solutions UU and HU will be linear and homogeneous in the mean fields, U mean and H mean enthalpy. And as a consequence, the mean force and the mean source, they will, as here notated as functionals of the original fluctuation, the background fluctuation, those fluctuations which are seen in the main run and the mean fields, we find that these functionals are now, again, like before, linear and homogeneous in the mean fields, which is, as I said, a prerequisite for any mean field for any test field method. And now it can be formulated by simply repeating the equations which already were shown before. But what I did is only putting the indices, and here we have to think about now test fields for H, for the mean enthalpy, and for the mean flow. The second derivative is there too.
S is gradient, right? S is gradient.
You have seen that, yeah?
Yes.
S is the strength tensor. Rate of strength tensor. Yeah. And then finally, when having resolved the system for the quantities U, K, and HK, one can determine for each of the test problems or each of the test fields, these two quantities, the mean motive force and the mean source. This follows completely analogously to the pattern shown before. Yeah, again, of course, because it's simple and good to make first steps. Coming to planar averages, that is again, in our cases, over x and y, and so the mean quantities are dependent only on z. And then, which are the ansatzes we have to make for the mean quantities, for the mean force and the mean source. Yeah, this is something like that, if you go to, at most, to second derivatives. And how can we interpret these different terms or coefficients? First, what we see here is clearly has to be associated with the turbulent viscosity. Then we have here a coefficient which goes with the curl, W is the curl of U, which goes with the vorticity, and that can be attributed to be a so-called kinetic alpha effect. Or it can even contain a contribution of a lambda effect if there is rotation in the system. It would be at the same place, they would melt together, it wouldn't be distinguishable. Then we had something at this place which makes a contribution to the turbulent pressure, or reflects turbulent pressure. We have something here which would contribute something to the turbulent sound speed, and this quantity which would represent turbulent transport of enthalpy. They could in fact all be determined, but I will not show that it except for the turbulent viscosity and the Aka effect. Yeah, results again for the same forcing type, for the robust geometry. Here I have sound speed 1 in our units. This value has mainly to be compared with velocity values, which appear in the text. Here's the Aka coefficient. And because we are kinematic, and there is no mean flow in the main run, then everything is isotropic, planarly isotropic, so because with respect to x and y isotropic, and there's only one value for the Aka coefficient and for the turbulent viscosity. The solid lines again show the Stockholm results, which can readily be obtained here, and the symbols again the numerical results, where red means negative and plus positive. So we see here the deviation starts from the soccer result, which is already qualitative, so in that it has the wrong sign. And here it is even more pronounced. Here the sign is correct, but some deviation starts already here and more stronger here, where the sign is different. But for the label again is magnetic, it's Reynolds number in this case. Reynolds number of the fluctuations, of course. For the small Reynolds number, we have complete agreement between the numerical results and the soccer result. Okay, well, what happens if we go to less compressibility, that is a higher sound speed? I put here the value for 10, and this is essentially a RMS value of the velocity, so it's clearly farther away from the sound speed. And again, we have here the solid lines of the soccer results, which really show already the sign change for the Aka effect. But here's almost complete agreement, except at this one spot, where for the highest Reynolds number, the sign of the turbulent viscosity is indeed negative. But negative turbulent viscosities are known. These are not completely a surprise, because there are several even analytic results which show that turbulent viscosity can be negative. So it's not unphysical. But that is not really small. For small not. You see, everything is positive. It's not really small. Sorry?
Is it for large Reynolds number negative?
Yeah, this is in the order of 1.
No?
It's already no longer small. No. So this teaches, at least me, that the validity range of second order correlation approximation in this case has to be defined not only by the Reynolds number, but in addition by the Mach number, which somebody of you might say this is trivial, but I have learned it at this place. Is positive. Total viscosity is positive. Yeah. Yeah, hang on, if we go back. Because both results have indicated there's clearly an Aka coefficient. And here too, of different sign. So it indicates Robert's flow has the potential for the anisotropic kinetic alpha effect, and maybe then there is an instability based on this effect. So I was guided by these results. I started to search for it, and it was easy to find. In that sense, the test flow or test field method has already produced a predictive result, because it predicted me where to look for this Aka instability. And I've done one simulation, or indeed several, where I've seen this behavior, fast exponential growth of a mean field. This would be really be a mean. Oh no, sorry, it contains a mean. I know this. And then a slow, starting on the first plateau, and then a slow on a resistive timescale effect of appearing saturating process, which then comes up to a constant value. This is in a vertical plane, xz, the modulus of the velocity vector, and this is the mean field. And both components, the x and the y component, are shown here. Because the solution of this Aka instability, or if you want hydrodynamo, is again a Beltrami flow. It has x and y component, and they have to have exactly the phase shift which is obtained from the direct numerical simulation. This is a direct numerical simulation, and the mean field model, using the coefficient which I have shown before, would yield exactly the same. And finally, I've done first steps into cases where we have rotation in the system. I have fixed here the sound speed to 1. And I show here now 4 different panels, because by the influence of rotation, there are now off-diagonal components possible in the tensors, because the rotation clearly introduces anisotropy. And the background is already helical. So by this construction principle, you would get off-diagonal components, and they are shown here. They have to have different signs, because this is creating a completely anti-symmetric part. You see that? This is exactly satisfied by the results here again for mu. And these are the main diagonal components, which need to be identical, which is exactly the same for the numerical results. And we see here again that the turbulent viscosity might change its sign for higher rotation rate at this place. Here it is pretty low magnetic, pretty low Reynolds number, but I could not check this range for numerical reasons for these curves for higher Reynolds numbers. So I really don't know what happens with the sign of the, if we would proceed in this way, in this direction. At least in this one case it is shown that, again, the turbulent viscosity might change its sign. Yeah. So let us assess what we have found in the test method for hydrodynamics. We have, as far as available, agreement with Soka results. It was demonstrated that the range of applicability of the second order correlation approximation depends on the Mach number strongly. And there was an AKA effect predicted, where I had not supposed to find one before, but it's due to my ignorance, maybe. But it has proven to have a predictive potential at this place. So as a conclusion for both of these methods, I would say they are so far encouraging. We have not a complete scan of the nonlinear realm. We don't know what really happens if we go farther away from homogeneous fields which influence the flow and so on. And we, of course, most interestingly, we had to study the case of real turbulence. So say of delta correlated in time force turbulence, which we could easily do in numerical simulations. But some first attempts showed that it is not that an easy game to figure out the turbulent viscosity, say, for the case of turbulence. So these are many open questions, but I would like to stress once again that at least I feel encouraged by these results. Thank you.
This is the same Okai effect which was studied by the
Yes, basically yes. Yeah.
So this effect will likely be increased with Reynolds number?
I think so. But I can only speak about the range I have seen. As far as I have scanned, the Reynolds number range is survives. Doesn't disappear.
Matthias, you have always considered the XY approach, so that the mean fields depend only on Z.
Right.
Under this assumption, you can represent the derivatives of E, for example, but by the current.
Right.
It's no longer possible if, for example, the mean fields depend on two coordinates. Yeah. I guess it is not too difficult to write all this down, or suppose it's more general case. It is so.
Yeah, it remains mainly true up to the very end, where we then specify the test fields. So if we have cases like, for instance, that we have means which depend on one coordinate, say on y, then we all of a sudden need more test fields. But that's not an obstacle at all. And it has been done for the quasi-kinematic method already. And there's no reason why one could not extend the same technique to these methods.
The first application of the test field method was with phi averages.
That's true. That's true.
The strong magnetic quench you observe to the power of 4, could that be a result of the simplified momentum equation?
Sorry, of the simplified? Oh, I see. No, it was already seen in other simulations for the ABC flow, where no such approximations or simplifications were done.
Yeah, I was guilty, so to speak, because that is in a paper with Kanaswamy Subramanian, Shania Shu, and myself. We did have a plot where we got the data and we put next to it a b to the -3 line, and we argued that there was agreement. But if because we expected k to the -3 based on the early result by Moffat. But if you actually put a b to the -4 line, that is spot on. So that the b to the minus 4 line really fits. The b to the minus 3 line doesn't fit. And I was at the time really just thinking that there's a minor departure. But the correct result is therefore b to the minus 4 for the ABC floor with the full nonlinearity.
So this would be a counterexample to any.
Yes.
Thank you. Thank you for very interesting talk. I listened to your talk with wondering what is the essential difference between the green function method with the test field method. In my understanding, so test field method, test field equation can be non-linear. Is it?
No, the test field problems itself, they must be linear.
Must be linear.
Because otherwise, these test solutions would show an imprint of the test field, and they are not allowed to do that. They should represent properties of the real turbulences, and not any properties of the test fields. That's why they need to be, the test problems need to be linear.
Okay, so another point is...
The actual physics problem is fully nonlinear, of course.
Yeah, okay. So another point is that the test field equation can treat the arbitrary magnitude of inhomogeneity. Is it right?
So the inhomogeneity in the test problems, the amplitude of this is without any meaning. It's simply a scale factor which would be divided out again at the end. But maybe your question is referring to the strength of the mean field in the main run, in the real physical setup. And so the method itself should not be limited by that. But of course there are numerical limits.
But conceptually...
Conceptually not. I would not say so.
Application of this approach to nonlinear case. So you said that scaling for alpha is magnetic field in the minus 3 power.
Minus 4 what we see.
Yes.
What we see is always minus 4.
This result, at least theoretical predictions, is b minus 2 power.
It depends either. It may be
Yes.
minus
But
2.
what about the scaling for magnetic diffusivity?
We haven't checked that.
You haven't.
I cannot say. I cannot tell you.
It's minus, I can maybe enter, it's minus 2 for time-dependent flows, and minus 4 for non-time-dependent flows.
Maybe even minus 3 and for turbulence. In case that relation time function of magnetic field, in this case, theory predicts minus 3. And it's no result of Günther.
I know, yeah. But here we have very clear conditions. So this, the flow is laminar and regular, and everything is stationary, and the result is again very clear. There is no doubt that it must be that steep slope.
Okay. Matthias, could you, in the meantime, compare your work or your results to what others Courvoisier already did? Is there some comparison already?
Sorry, who?
Alice Courvoisier.
Of course, we have seen the papers of her, but we found that there is no direct comparison possible.
But that's because they use full hydro, full the U cos omega term in the hydro.
We have here this model problem, which is the wrong physics in some sense. So we have to set up the same quite analogously for the real NHD. I have not done it. I have done it for the hydrodynamics with proper physics, what I showed you, but not for MHD, simply by what laziness or lack of time or lack of power or whatever. It should be done.
So, more questions?
Okay, let us thank Matthias again for very Our next and last speaker today is rheinhardt+plunian, transition from large-scale to small-scale dynamics.
Hear me? Yes. So the job of the last speaker is always to wake up everybody before leaving. So I hope I will manage it. Okay. So I will talk about transitions from large scale to small scale dynamo. So I apologize for the people who are in Carges because I more or less repeat what I have told that time. But I think it was a good opportunity to present these results to Karl-Heinz. So this work was done in collaboration with Yannick Ponty from the Observatoire de Nice. It's pretty unusual to see some snow on this hill, but okay. And on the background, you can see some mountains. So I'm sorry because I know that Frank already presented this yesterday, but I will repeat it maybe in a different way. So here you see the Aiguille du Midi, which is a mountain just above the valley of Chamonix, which is that you can go up by a cable car. And from it you can see several mountains, Mont Blanc du Tacu, Mont Maudit, Mont Blanc. And you can also go from there to the top of the Mont Blanc, going through this, all these summits. And you can also either come back by the same trail or go back by this route, which goes to Le Refuge du Goûter and then Chamonix again. So the link between l'Aiguille du Midi and mean-field electrodynamics is not clear, unless Frank, Stephanie, and Karl-Heinz remember that we, in fact, we met almost for the first time on the top of the Aiguille du Midi. It was in 1997, and so it was during a Pioneer conference, and I was in charge of organizing this trip. So there was also Jutta, the wife of Karl-Heinz, and Martin Collet and his wife, and I think also other people, but I don't remember who was with us. Anyway, on the trip back to Ossois, we started to discuss with Karl-Heinz about dynamo effect and other things. And then at that time I was looking for a postdoc, so he invited me in Potsdam. I gave a seminar, and a few months later I was in Babelsberg to spend some beautiful time in as a postdoc. So if I remember well, but tell me if I'm wrong, Matthias, this was your office? There?
Along with the pizza.
Was it?
To the right,
Okay, and anyway, my office was close to yours, and we had endless discussions during the night, especially. And I remember I liked to cross the window and walk on this balcony, smoking my cigarette. I was a smoker at that time, watching the stars and thinking about in-field electrodynamics. And at that time, the life was kinematic. My life was kinematic and laminar. It was 2 years before the success of the Karlsruhe experiment. And so we, in the group of Karl-Heinz, there were intense work activity to make predictions on this experiment. And as a postdoc, my job was to take into account the finite size of the device. So the size in the vertical direction and also in both horizontal direction. And so we ended up to study the subharmonic solutions of the GeoRobots dynamo. Okay, Matthias already explained to you what it was, but just to show you what it looks like. So you have some holes, which are helical, and here I plotted the magnetic field lines which are generated by these holes. So they are helical, so they are horizontal, and they turn like this. And when you take into account this finite size of the domain, so you end up with some marginal curves in terms of Rm versus the wave number k. And the curve A is for an infinite number of cells. The curve B is when you have a ratio equal to 10 between the flow cell and the device. C, a ratio equal to 8, 6 and 4. And one interesting thing is that if you take, for example, a wave number 0.1, so the vertical wave number 0.1, you see that you have only a window in which dynamo action is possible. Below, it is not possible, and above, neither. If you take into account, if you consider an infinite number of cells, you always have a critical magnetic Reynolds number, and it is always possible above. And so, in terms of parallel magnetic Reynolds number and perpendicular, so it means horizontal magnetic Reynolds number, this makes some corrections for the experiment. So A is the curve when you consider an infinite number of cells, and B is the curve when you consider the ratio of the Karlsruhe experiment. And so again, for a given horizontal magnetic Reynolds number, say equal to 2, you have between 2 and 1, you have a minimum Rm parallel for which the dynamo becomes possible, and then a maximum here. The nice thing with the GeoRobots dynamo is that when you split the induction equation in mean part and fluctuating part, so you end up with a mean electromotive force like this. As the flow does not depend on Z, each vertical magnetic mode is independent from the others. And so, in fact, you can calculate independently the electromotive mode, the mode of the electromotive force like this. And you can show that it writes in terms of an alpha tensor times the mean magnetic field. And alpha turns out to be very simple, only these two terms. So in fact, you can write that epsilon is proportional to the mean magnetic field with a coefficient alpha. And then, so this is completely due to the geometry of the flow. And then you can write that the growth rate of the magnetic field is governed by this alpha term. And in addition, you have the dissipation curve. And when you plot this alpha hat terms for versus k, the vertical magnetic wave number, and for different magnetic Reynolds number, so 0.25, 0.5, 2, 1, 4, 8, 16, 32, 64. This is what you find. And coming back to what Matthias said just before, you see that provided that Rm is smaller than 1, we have straight curves like this. Okay, but when Rm is larger than 1, then the curves are not straight anymore. And in fact, when you can also write the mean electromotive force in terms of an alpha effect in the traditional sense, beta effect, which is the turbulent diffusivity, and in fact, this alpha coefficient and the turbulent diffusivity correspond to the value of alpha hat at k equals 0. So this is alpha for Rm 0.25 and so on, 0.5, 1. And you see that, so these curves are completely described by these two coefficients, provided that Rm is smaller than 1. So meaning that the Soka approximation works in here only for magnetic Reynolds number smaller than 1, which is what you said just before. And you can also plot this coefficient, alpha for k equals 0 and beta for k equals 0, versus Rm. And what we find is that it is decreasing versus Rm, and it scales as Rm minus 1/2. And provided that the magnetic Reynolds number is sufficiently large, larger than 1, then you find a negative turbulent diffusion. And this was explained in 2 papers that we published in 2002. Okay, so this was what I did during my postdoc, but at the same time and the years after, we also had an interesting discussion with Karl-Heinz, Matthias and others concerning the following problem. If you write the induction equation and split it in mean part and fluctuating part, in fact, we understand that concerning the mean part, on the left-hand side, we have a function which is linear in B bar. Okay, and here we have also a function of small b, which is linear in B. And the difference between the two equations is that the kernel of this function is 0, meaning that if you suppress what is on the right-hand side, then B bar will decrease to 0 because of diffusivity. This is what I wrote here. The kernel of L is 0. And so you can write that B bar is L minus 1, this term. Okay? But for the second equation, this is not the case, because if you suppress what is on the right-hand side, then you may still have some dynamo action known as the small-scale dynamo. Okay, because you have here all the terms for dynamo. So it means that the kernel of this functional L is not 0, and so that small b writes like L minus 1 this term plus some additional terms which satisfies L of B0 equals 0. Okay, so this means that you can write the total magnetic field like the sum of a mean magnetic field plus a small b which derives from the mean magnetic field plus a small b, which exists even if b bar equals 0. So this is why here the superscript is 0. And then you can calculate a mean electromotive force deriving from b bar plus something else which may exist or not, even if b bar is equal to 0. And this has been noticed by Karl-Heinz a long time ago, in 1976, in a paper. And recently he wrote this again in the frame of history of MHD. Okay, and so we can, what I understand of large-scale dynamomechanism is when these two terms don't exist, meaning that only B is the sum only of B bar and small b deriving from B bar. So in this case, small b derives from B bar derives from small b, and then B and B bar feed each other. And then we can calculate and make predictions in terms of mean field theory. And probably test method as well. But there is another case when we have dynamo action without, or yes, suppose for example that B bar is 0 and we have then the apparition of a small b. Then in this case small b equal to b 0, but then you still may have a mean magnetic field deriving from a mean electromotive force, this one. Okay, so at the end you will have this large-scale magnetic field may create a small-scale magnetic field B bar, but maybe there are some cases where these two terms will be small compared to this one. And this is what I would like to investigate in the rest of my talk, and what we did with Yannick Ponty. And the transition between both.
This is really dimension 4?
No. What do you ask?
Your dimension is...
No, it is on dimension form. It is not dimensionless. You have, you see, you have the diffusivity is included in the functional L. Okay, so to study that, we considered a fully nonlinear problem composed of Navier-Stokes equation and induction equation. We used a parallelized spectral code and we made calculation in a periodic box. So this periodic box is not cubic, it is a parallelepipedic, and it has a height which is twice the horizontal direction. And for that we use again the Roberts forcing to make the flow. And so first we calculated the dynamo onset. So here we plotted the magnetic Reynolds number versus the Reynolds number. So there is dynamo action above the marginal curve. So this horizontal line corresponds to the prediction of the kinematic laminar theory. And what we observe is that for intermediate values of the Reynolds number, the critical magnetic Reynolds number jumps to a maybe twice high value, and then goes back to almost the same value as for laminar case. So this is how we understand this. So on the left, in the laminar case, so the rows are really the Roberts, correspond to the Roberts rows. And here we plotted the magnetic field lines. at high Reynolds numbers, here we plotted the time average of the rows. And you can see that again we find almost the Roberts flow, the laminar Roberts flow. So in fact it seems that the fluctuations of the flow don't play such a big role in the calculation of the critical magnetic Reynolds number. It is more the long time behavior of the flow which is important there. And in between, we were never able to calculate an average flow because there is some instability and the flow never is not stationary on average. It always moves. Okay, so we understand this this bump as the effect of this hydrodynamic instability. And this has been indeed shown in previous studies that large-scale hydrodynamic instability can increase the critical magnetic Reynolds number. Okay, so the thing to remind is that for this large Reynolds number, the threshold is controlled by the long-time coherent flow. We also found that most of magnetic energy corresponding to this curve is in the mode k equal 1/2. So the other modes in k are not so energetic. So again, we can apply the same formula that we did for the laminar case. So calculating the mean electromotive force for this mode k equal 1/2, so it corresponds in Fourier modes to the modes 0, 0, 1/2. Okay, 0 in x, 0 in y, and 1/2 in z. We can, so the code also gives the same mode 0, 0, 1/2 for the magnetic field. And so we can, from these two quantities, we can calculate some alpha tensor. Of course, it is highly depending on time, but we can average it on time. And we find that alpha 11 is on average equal to alpha 22, and the two anti-diagonal terms are almost zero. So, finally, at the threshold, we find that the previous relation that we had for the laminar Roberts flow still controls the large-scale dynamo mechanism. So we conclude from that we are in that the dynamo mechanism at the threshold is large-scale. So it can be explained by a mutual feeding between small b and large b. And so what we did after is that we fixed the Reynolds number to such large value, and we increased the magnetic Reynolds number as far as we could. So this maximum point, I think, corresponds to magnetic Prandtl number equal to 1, and this is lower than 1. So we fix the viscosity, and we vary the diffusivity. So this is some example of what we find. So this is just above the threshold. So in blue it is the kinetic energy. In red it is the total magnetic energy. And in magenta it is the energy in the mode 0, 0, 1/2. So the mean field mode. And we see that almost all the magnetic energy is in this mode. Okay, both curves are almost the same. And here we see large structures of the magnetic energy. And in comparison, when we increase the magnetic Reynolds number 45 times the critical Rm, so in fact the mean magnetic energy doesn't change much, but the rest of the energy is almost equipartition with the kinetic energy. And we see that the scales is much smaller. So again, versus Rm, we plotted the ratio of total magnetic energy versus kinetic energy, and we see that when we increase Rm, we find almost equipartition. And here it is the ratio of the mean magnetic energy to the total magnetic energy, and we see that it decreases versus Rm. So it seems that we are not anymore, at the end, in a case of a large-scale dynamo mechanism, but maybe more a small-scale dynamo mechanism. So to illustrate this, I show you some movie. So in blue it is some kinetic spectra of the kinetic energy. In red, the magnetic energy. So we see that it is growing at small scale. Here it is growing at large scale. And so close to the threshold, the magnetic energy stays peaked at the larger scale. But in the other case, so it varies, but it is not so much peak. It is rather peaked at a smaller scale here. So we checked out that most of the mean magnetic energy is still in the mode 1/2. And so for this mode we can again calculate from the code. The code gives us the Fourier mode for the mean electromotive force, for the mean magnetic field, and so we can calculate the coefficient of the alpha tensor. And this is what we find. So the top row corresponds to alpha 1,1, the second one to alpha 1,2, alpha 2,1, alpha 2,2. And for each column corresponds to a different magnetic Reynolds number. And so from left to right, the magnetic Reynolds number is increased. So let's first focus on the first line, so alpha 1,1. We see that close to the threshold it is this is the kinematic regime, this is the dynamic, the saturation regime. So it is equal to minus 0.25, and okay, again, and then it goes to smaller and smaller value. So in black it is some average in time that has been done on the coefficient. So it is almost 0. The coefficient alpha 1,2 is always about 0. So here it is this case is a bit peculiar because we have some signal which is quasi-periodic. But you see it is always almost 0. Here, alpha 2,1 is the same as alpha 1,2, and alpha 2,2 is almost the same as alpha 1,1. And so when you plot these four coefficients versus Rm, so the two diagonal terms decrease as Rn minus 1, and the two anti-diagonal terms first grow and then decrease in Rm. So again, it seems that such coefficients are not sufficient to describe the dynamo mechanism when Rm is much larger than the threshold. And I want to emphasize the fact that contrary to the previous talks, here this coefficient contains the traditional alpha effect plus the turbulent diffusion plus all other terms. So we didn't try to calculate separately each term. Okay. Yeah, so it seems that at dynamo onset, it is more a large-scale dynamo mechanisms which governs the dynamo action, and much above dynamo onset, it seems that it is more a small-scale type of dynamo mechanism. But to be sure, yeah, then we can ask the question, does this B0 term exist even without B bar? Because, of course, in a numerical simulation, all the different quantities are completely mixed, so it's difficult to sometimes to be sure of that. So what we did to try to answer to this question is to set at each time step B bar equals 0. Okay, so at some time step we set B bar equals 0, then we calculate the flow and the magnetic field, and then of course there is some B bar which is coming out, but then we set it again at the time step after to 0, and so there is no B bar at all in the calculation, and this is what we find. So this is so in red, in blue it is the kinetic energy and the magnetic energy. This was the previous case, solving the complete problem, and the dashed line corresponds to the case with B bar equals 0, so without mean magnetic field. So if we look at the magnetic energy, we see that the threshold, the dynamo threshold, is delayed to much higher magnetic Reynolds number, so which indicates that in these cases the mean magnetic field plays an important role in the nature itself of the dynamo action. But for large enough magnetic Reynolds number, we find some dynamo action. Of course, what we can see is that this dynamo action is not as efficient as in the case where you consider all the magnetic field. So it seems that we find some small-scale dynamo, but this small-scale dynamo cannot act alone, and in this case, the mean magnetic field seems to play some role still. Okay, I will maybe skip this. So in conclusion, so I repeat a bit myself. I dynamo onset so B0 equals 0 and B bar is much larger than this part, and much above onset B0 is not 0 anymore, and B bar, we find that B bar is smaller than the two others. So far it is not clear how this transition is related to PM, because in fact the last 2 points correspond to PM equal 1 and 2. But in DNS it is difficult I mean, if we want to study smaller values of PM, then we have to increase the Reynolds number, and so it makes the thing difficult. So then we looked at other examples in literature. So this is a paper published by Axel in 2009, and so he used helical isotropic forcing for different magnetic Prandtl number. And what we see that in each case, he always found spectra peaked at the larger scale, which can be seen here in the magnetic energy representation. Okay, so it seems that in this case is always in the case where the dynamo mechanism is large scale. So maybe Axel, you can tell me how much were you above the dynamo onset in your calculations? For example, here I think the magnetic Prandtl number is quite low, but okay. Maybe this is something to understand. And I was
4.4 is the smallest magnetic.
4. Yeah.
Probably bigger than 1.
Yeah, of course, yes. But how much supercritical? 4 times.
4 times,
yeah. Okay. So because we had to be, yeah, better. And so probably if you would play the same game as we did, you would not find a dynamo, I suppose. if you set b bar equals 0. And in the others? You would?
I think so. Number 1, you get small scale animation.
Yes.
At 35, in Reynolds number 35.
But you still find a large scale dynamo mechanism here.
Yeah, we don't put b bar to the 0.
Yeah. Okay, so anyway, this is but so you are much above onset here. Yes. So maybe the reason is the following. This is a multiple scales model derived by Frick, Stepanov and Sokolov in 2006. So they, as in the talk this morning, they considered a large scale dynamo model with some an alpha square dynamo and a shell model for the small scales, and so the alpha term are given by the magnetic helicity and the kinetic helicity of the shell model. So in all these plots, so from top to bottom it is a growing helicity, and from left to right it is a growing scale separation between the large scale and the small scale shell model. And in our case we have a strong helicity. So let's look at the last row. When we grow the scale separation, we see that the large scale magnetic energy, which is in black, is going up. So until equipartition. So maybe we are in this case where the scale separation is not big enough, and so we should try to have a thinner Roberts rolls like this. So k equal, I don't know, 1/4 or 1/8, and then the dissipation, the magnetic dissipation of the large scale magnetic field will be smaller. And so maybe some large-scale dynamo mechanism will be possible again. And this is my last slide, and happy birthday, Karl-Heinz.
In these simulations you have forcing in the form of Roberts flow, and the coefficients of the Roberts flow, before multiplying by the Roberts flow, they are random or not?
They are?
Random or
No.
constant?
The forcing is a constant forcing. Constant in time.
Constant in time.
But as we have small viscosity, the flow is fully turbulent. So the flow is, in some sense, has some strong turbulence.
The mean magnetic field can never grow faster than the resistive time, because the domain is closed and you have to fight against the total magnetic helicity build-up. Did you run for several resistive times in the highest
Yes,
cases?
we would check this out, yes. Because we discussed this in Carles, and since then we did this. It doesn't change the results.
But is it that the mean magnetic field at first grows and then has a crash, that it breaks down after it has grown to some not too small value and then it crashes?
I think not. I think he never, if you look, for example,
No more question.
you see, if you look at this curve, the mean magnetic field always stays here. It is this is the kinematic regime, and it is the small scale magnetic field which grows up.
How much is the resistive time here?
No, but I don't remember, but what I can show you that we prolongated this calculation to several since Carges we did this. Because I know that your argument would be that this could grow slowly, but because this is what you find, but this is not what we find.
And the box was still not big enough, not enough scale separation.
Yeah, this is what. Yeah, maybe.
Yeah, simple question. You said that the alpha coefficient you showed contained everything. The turbulent diffusivity too. And then I would expect that this coefficient is complex.
Oh, they are.
It was simply the modulus of some that you showed.
They are complex.
They are complex, okay. And even that there is very likely a small scale dynamo now, there is a background magnetic turbulence or fluctuations. Then what's your method to measure the alpha then? Because I've just spoken about this situation before.
So again, we don't measure the traditional alpha effect. We rather measure such coefficient here, alpha hat. Just
nevertheless.
So the code gives us the mean magnetic field. So the Fourier mode 0, 0, 1/2. Okay, and we calculate the U cross B, and we take the same Fourier mode of this quantity. And so we say that epsilon is equal to alpha B bar. And then we end up with the 4 coefficients.
Okay, but this is a tensor. Is it tensor?
Is it what?
It should be a tensor.
It is a tensor. Yeah. But in fact, the mean, the Z component of the mean field and the mean electromotive force are 0. It stays in the Roberts geometry.
I see important difference between your results and auxiliary result because of the turbulence in your cases seems to be anisotropic. You have some reference direction, and maybe because of non-local. In your case, you have stronger non-local scale interaction between large scale and dissipation scale, and this is why it's difficult to compare exactly the dynamics of large scale and small scale. And can you check out in your simulation how strong this anisotropy and how strong the non-local energy transfer because of this anisotropy?
So
in principle,
it is strongly anisotropic.
Yes.
In our case.
Due to this anisotropy, do you have some amplification or maybe some non-local energy transfer because of this? Because as I understand, actually, in your case, you have your forcing is isotropic.
Yes. So maybe it is a difference. Yeah. But to check it out, what do you mean by checking out?
I mean, why? Okay, maybe the main difference between that you have the case with if you far above on the offset of the dynamo and close to the offset, you see the different scenario of this.
Yes.
Okay, just remark maybe.
But it is important because, for example, in the case of the Earth's core, the flow is, as Paul Roberts showed this morning, is also strongly anisotropic due to the strong rotation.
And in your simulations, do you have separation of scales? So forcing scale in much smaller than the size of the box or not?
No.
There's also a difference between your simulations and Axel's.
Yes. We have typically we have this. But of course it would be nice to have several more, but then it is more demanding for numerical calculations.
How these simulations can be different from ABC forcing? So basically the form of ABC flow.
So ABC is more isotropic, and but basically I think maybe it would be comparable. I don't know.
Well, I'd just like to say that I was briefly looking around at Robert's flow, and if I included only 4 full cells, so twice your spatial extent in the horizontal plane, I think, I was already seeing strong effects of the anisotropy in the horizontal plane in the nonlinear case, even out to, I think, is even to 9 full cells. So the saturated case was not an alpha squared dynamo with Beltrami field. So I would really look into increasing your spatial extent there.
Yeah.
I
So
guess.
you mean taking more than only 4 cells?
Well, is that 4 full? I mean, I consider full cell to be the full 4 columns.
4
Is
columns,
is one cell, I'd say.
Well,
that looks like one cell to me.
This is one cell for you.
I think, if
Okay.
I'm reading that correctly.
Okay, so you take 4 of them.
4 of them.
And then you find that it is...
And then even at 4 cells, I think I have to go to a vertical wave number of 2 to get dynamo action. And you see anisotropy in the saturated regime. But that's something that I was looking at only very briefly recently, and then I got distracted.